Hello Algebra 2 and welcome to the Chapter 6 and 7 Review Number 1 video. You do have skipping abilities, so if you know how to do these problems, you can skip ahead to see what the answers are. Problem 1 gives us this very odd periodic function. Periodic means it repeats periodically, and notice that I have 1, 2, 3, let's go yellow, 4 complete waves up here, or 4 complete repetitions. Let's see, when it asks for what the period of the wave is, that means how long one cycle takes. And so let's see, if I'm starting here and finishing, I'll get the yellow pen, if I start at this dot and finish at this dot, it takes me 1, 2, 3, 4, 5, 6, and you could check to make sure that all of these guys are 6. 1, 2, 3, 4, 5, 6. Sure enough, the period of the wave is 6 units. How many complete cycles are shown? Hopefully you see that there are 4 complete waves. 1, 2, 3, 4. Complete cycle is a complete wave. And what is the amplitude of the wave? You're used to seeing amplitude as for sine waves, where the amplitude is that A value, or how far up and how far down. Fact of the matter, amplitude is displacement from the center. And so if I'm looking at this wave, maybe I'll clean up this first red one. If I'm looking at this wave, the bottom is at -2 and the top is at 5. So this distance is 5 plus 2 is 7. The amplitude then, or the middle, would be up at 3.5. So the amplitude would be a displacement of 3.5 in either direction. Amplitude 3.5. Moving on to number 2. Rewrite this thing in graphing form and sketch it. Well, I look at this equation and I think it's going to be a parabola. Parabolas look like y equals a, parentheses, x minus h squared plus k when they're in graphing form. And so I need to complete the square. I'm going to start by pulling a 2 out of the first 2 terms. So y equals 2, parentheses, x squared minus, well, if I factor out a 2, that's now a 2x minus 3. In order to complete the square, I need to figure out how much I need there to make a perfect square. And so I'll harken back to Algebra 1 where we made perfect squares. We had an x squared in the lower left. We had 2 negative x's, and we placed 1 negative x in each spot. And we figured out what the sides would have to be to make a perfect square, x and -1. And -1 times -1, now they look like exclamation points, is +1. So we need a +1 to make this square perfect. So I'm going to go ahead and put a +1 there. But what I just added to this equation is 2 times 1. So I just added 2. So that means at the end I'm going to have to subtract that 2, so that I really haven't changed the equation at all. But now I can write this in perfect square form. This is 2 times a perfect square. And the perfect square is x minus 1 by x minus 1. X minus 1 squared with -5 at the end. So here's my equation in graphic form. Looks like I need an equal sign. I'm going to graph this thing. We have a vertex at 1, -5, so 4, 1, down 5. And it is stretched by 2. So normally, when graphing a parabola, I'd go over 1 up 1. But now I'll go over 1 up 2. Back 1 up 2. Normally, I'd go over 2 up 4, but now I'm doubling that, so over 2 up 8. And back 2 up 8. We've got our 5 points, so I'm going to connect them and make it look parabola-ishy. Moving on to number 3. Number 3 has a bunch of review problems. Let's see. There's this crazy log problem, and logs scare me, so I think it might be nice to rewrite this in exponential form. Since the base of this log is 3, log base 3, that means I'm going to change this to 3 to the power, and my exponent is the answer, so 3 to the 4 has to equal 5x plus 1. 3 to the 4th is 3 times 3 times 3 times 3, or 9 times 9, so 81 has to equal 5x plus 1. If I subtract 1 from each side, 80 equals 5x. You could whip out a calculator if you needed to, but I prefer just to do it in my head. I think 5 fits into 80, fits into 160 10 times, so it fits into 80. I'm sorry, 100. Sorry, I don't know how my brain was doing this, but I just go 10 goes into 80 8 times, so 5 goes into 16 times. That's an answer. That's what I was thinking. Number B has a bunch of fractions, and I don't like fractions much. So what I'm going to do is multiply both sides of my equation by something that will eliminate all the fractions. And I need to eliminate a 3, an x times x, and a 3 times x. And I'm thinking 3x squared ought to do the trick. So I'm multiplying both sides of my equation by 3x squared. And I'll do this in baby steps. If I multiply 3x squared times this first term, I'm going to get 3x squared times 2 divided by 3, minus, multiply 3x squared by the second term, it's 3x squared times 7 divided by x squared, equals, and if we multiply 3x squared times this chunk, I get 3x squared times 1 over 3x. Well, the whole point was to cancel these fractions. And so if you skipped this step, I don't blame you a bit. In this first fraction, this 3 cancels that 3, and I just get 2x squared. In the second fraction, x squared cancels x squared, and I get 21. Equals, and here 3x cancels with 3 and one of the x's. So my answer is 1 times x. In order to solve this, I have to set it equal to 0. So I get 2x squared minus 1x minus 21 equals 0. And if I factor this thing, 2x squared has to be a 2x and an x. I have a good feeling about 7 and 3. So if I try 7 here and 3 here, 7 times x is 7x. 3 times 2x is 6x. If the 7x is negative, they do combine to negative 1, so I'll make this negative and this positive. All right. Now all that's left is to solve it. Here, either 2x minus 7 would be 0, or x plus 3 would equal 0. So x would equal negative 3, or add 7 divided by 2. X would equal 7/2. And we have an answer. Ready, set, number C. And for number C, let's see. We know a couple of angles. We could find this third angle because they have to add to 180. And that might be a wise thing to do. 75, 75, and 61. Well, that makes 136. And so 180 minus that, minus 136, would be 44. So this angle here has to be 44 degrees. And I think we're just ready to go. It looks like since this is not a right triangle, we'd have to use a law of sines or cosines. I happen to know an angle and its opposite side now, and another angle and its opposite side. So maybe you remember that you could take the sine of an angle over its opposite side, and that would equal the sine of another angle over its opposite side. So I could say sine of 44 degrees over 10 has to equal the sine of 75 degrees over x. And maybe to solve this thing, I'll do a little cross multiplication action. X times sine of 44 equals 10 times sine of 75. We could divide both sides by sine of 44. Divide by sine of 44. At this juncture, it's time to get the calculator out. Get it clear, and I have to go 10 times sine of 75, and then divide by sine of 44. I should just check and make sure I'm in degrees. I am. And close parentheses and hit enter. It tells me that side, that my x is in 13.90. Leave it at that. Moving on to number 4. Without using a calculator. Give exact values. I tell you, people, the best way I think to do these things is to draw the angle. Draw the angle in a circle. So for each one of these, 30 degrees, well, 30 degrees is right there. So that's a 30-degree angle. So we have a special triangle. And let's see, what I know is that the cosine is the x value. And if I have a 30, 60, 90, like so, 30 and 60 and 90, and my hypotenuse is 1, remember that this short side looks like exactly half of the 1. So this is 1/2, and the only other number you need to remember is root 3 over 2. So the answer to A, the cosine of 30, is this red distance, which is root 3 over 2. Cosine of 90. Well, cosine of 90 degrees is all the way up here. There it is. And the cosine is the x value at this point. And the x value, the back and forth value here, is 0. Sine of 225 degrees. Well, 225 degrees, I know this is 180 degrees around. So 180 to 225 is another 45 degrees. So we're looking at a 45, 45, 90 triangle. And when you have a 45, 45, 90 triangle, you have two of the same sides, which is why it has a square root of 2 in it. At least that's the way I remember things, is root 2 over 2. So that means this side here is root 2 over 2. But wait, meaning that's the sign, the y value. But wait, it's a negative y value. So we're going to say this is negative root 2 over 2. Tangent of 135 degrees. Here we go. 135 degrees, well here's 90. And 135 is 45 more than that. So here is 135 degrees. And the tangent, hopefully you remember that the tangent of an angle, is the sine of the angle over the cosine of the angle, or it's the y's over the x's. And so I need to know the blue height, and I'd also need to know the green width. But 45, this is a 45, 45, 90 triangle because this angle here is 45. So we know that this cosine has to be negative root 2 over 2. And this, because it's backward. And this sine has to be positive root 2 over 2 because it's up. And so if we take the sine over the cosine, what we're going to get, we'll pause and make some room. There we go. What we're going to get is the sine, which is the y value, root 2 over 2, over the cosine, which is the x value, negative root 2 over 2. And we're dividing anything by itself, but it's a positive divided by a negative, which makes our answer negative 1. So this does equal negative 1. Moving on to part E. Part E says, okay, now we're in radians. Again, I'm going to draw the circle for these things. That was a really good circle, I gotta say. 5 pi over 6 radians. Well, pi radians is 180. That's all the way over there. So pi radians is 180 degrees. So that means pi over 6 radians is 180 degrees divided by 6, which is 30 degrees. And 5 pi over 6 is 5 of those. So 30 times 5 is 150 degrees. So I have a 150 degree angle is 5 pi over 6. Which means if this is 150 here, this is a special triangle. It's special because this angle here is only 30. So we've got a hypotenuse of 1. We've got that side is 1/2, and this is root 3 over 2. And what are they asking us for? The sine there. The sine is the y value, and so we can say it's 1/2. Cosine of negative pi over 4. Draw a circle. Let's see. Pi over 4. Well, pi is 180 degrees. Negative pi is negative 180 degrees. And if you divide by 4, 180 sliced into 4 even pieces is 45 degrees. So what we have is backward 45 degrees. Here we have it. Here's my negative pi over 4, or negative, I'll call it right here, negative pi over 4, or negative 45 degrees. Hey, 45 is special. It is a special triangle where the hypotenuse is 1, this side is root 2 over 2, and this side here is root 2 over 2. And this value here, the sine, is a negative value because we went down 2 over 2. What are they asking us for? The cosine. Well, the cosine is our x value, our back and forth, and so I'm just going to write my answer of positive root 2 over 2. Let's see, tangent of 2/3 pi. Okay, so I'm going to draw my circle, tangent of 2/3 of pi. Well, again, we know pi is 180. So 1/3 of pi is 180 divided by 3, it's 60 degrees. And 2/3 pi is 2 of those. So 2/3 pi is 120 degrees. All right, so I'm going to go 120 degrees. Or you could even think of, here's pi. 1/3 of pi is 60, and here's 2/3 pi. 2 pi over 3. And I just said that this angle here is 120 degrees, which means this angle here is 60 degrees. Again, it's special. It's a special triangle. My height is root 3 over 2. The base is, trick, negative 1/2 because we went backward. Since we want the tangent, you could either think of it as the opposite over adjacent, or you could think of it as the sine of the angle over the cosine of the angle. They end up being exactly the same thing. The sine of the angle is that height, it's root 3 over 2, and the cosine of the angle is that x value, which is negative 1/2. But that's not a very nice way to leave your answer. So let's clean that up. You could either multiply top and bottom of your equation by 2. That's a nice thing to do. Or you can flip and multiply. Multiply by 2 over 2. Those 2's cancel, and I get root 3 over negative 1. Also known as negative square root of 3. And last but not least, cosine of 3 pi. All right, well, there's my circle. And this far around is pi. And if I do it again, that's 2 pi. And if I do it again, I land here at 3 pi. So 3 pi is right there. We want the cosine of that, which is how far back our x value is. And that distance is negative 1. Moving on to number 5. Converting. Let me pause. All right. Well, we have pi over 8 radians. Pi over 8 radians, and we want it to be in degrees. So we need to multiply by a conversion that will cancel radians and give us degrees. We want to multiply by degrees over radians. That way our units will cancel, and we'll end up with degrees. So convenient converter. I happen to know that 180 degrees is pi radians. And so if I multiply these, I get 180 times pi divided by 8 times pi. And pi's cancel. And 180 divided by 8, well, let's see if I cut them both in half. It's 90 divided by 4. If I cut those in half, it's 45 divided by 2. So I get 22.5 degrees. 22.5 degrees. 260 degrees. So we have 260 degrees, and since I want radians, I want to multiply it by radians over degrees. And I happen to know that pi radians is 180 degrees. So when I multiply these things, I get 260 pi divided by 180. And we could divide the top and bottom by 10 and get 26 pi over 18. We could divide top and bottom by 2 and get 13
pi over 9, and I don't think it's going to clean up at all, so I'm just going to change it, leave it as 13/9 pi. That's crazy. 7 pi over 6 radians. So we have 7 pi over 16, rather, radians. And we want that to be in degrees, so I need to multiply by degrees over radians. Do you like that? It looks either like a D or the circle. I was going for the circle, but it looked more like a D. There. I happen to know that 180 degrees is pi radians. And notice my units are going to cancel. So I get 7 pi times 180. I don't know what 7 times 180 is, so I'm going to be lazy. Divided by 16 times pi. One thing I do know is that my pi's will cancel. And I'm too lazy to figure this out, but I'll show you how laziness pays off. 180 is 4 times 45. Oh, I like this. And 16 is 4 times 4, so we can do that. And now I'm too lazy to do this. 7 times 45 divided by 4. Where's that calculator? Oops, that's the video camera. We don't want that. We want this guy. It's 7 on. It's 7 times 45. Enter. 315 divided by 4. So I'm just going to leave it as 315 divided by 4. And that would be degrees. Oh, what the heck. Divide by 4. Enter. 78.75. Sure. 78.75. 75 degrees. Okay, number 11 is very confusing. It's confusing because it has a pi in it, but then it has the degree symbol. So what's it in, people? Well, if it has the degree symbol, it's telling you this is in degrees. And pi, in reality, is just a number. It's 3.14. And so 11 pi is about 11 times 3-ish. That's about 33 degrees. So 11 pi is just a number. It's about 33 degrees. We want to change it to radians, and it's going to be kind of weird. So in any event, I'm just going to go with procedure. I have 11 pi degrees, and I want to multiply by conversion, and that conversion needs to be radians over degrees. Well, I happen to know that pi radians is 180 degrees. And if I multiply straight across the top, what I get is 11 times pi times pi. 11 pi squared over 180. You could actually leave your answer like that. You could say it's 11 pi squared over 180. Or you could whip out the old calculator. Come on, calculator. Let's go 11 times, do we have a pi button on here? I think it's that blue thing. Pi, that's it, to the second. And then divide by 180. Enter. Tells me it's 0.603. Okay, I'm just going to trust them. 0.603 radians. All right, and last but not least, we have this 340 degree angle. So I have 340 degrees, and we want that to be in radians. So I want to multiply by radians over degrees so that my units, again, will cancel. I happen to know, and I bet you do, that pi radians is the same as 180 degrees. And so what we get is 340 times pi divided by 180. Again, I could divide by 10 on the top and bottom. I get 34 times pi over 18. They're both even. 2 goes into 34, I want to say 17 times, and 2 goes into 18, I know 9 times. So I'm just going to leave that as my answer. 17 pi over 9, and that answer is now in radians. Moving on to number 6. Aha! Number 6. We haven't done one of these for a while, so I'm going to refresh your memories as to my method for doing these things. I always label my equations so that my teacher can follow my work and give me partial credit in case I make a silly mistake somewhere. So we have equations A, B, and C, and we want to pick one variable to eliminate twice. And I wrote this problem, I made it kind of nice so that you could eliminate, pick x's, y's, or z's. Pick one. Let's go for y's. I like the y's. So I'm going to get rid of the y's. So that means I'm first going to take equations A and B and eliminate the y's. So that would be 3x plus y plus z equals 4, and x minus y plus 2z equals negative 2. By the way, you will notice that I cross my z's, and if you don't cross your z's, they end up looking like 2's, so it's a good habit to cross your z's. All right, now if we add straight down, those y's should be eliminated. If I add straight down, I get 4x plus 3z equals 4 minus 2 is 2. So I've got this equation. I'm going to hold on to it and pick two other equations to eliminate the y's. So now I'll pick, say, A and C. So A and C. Again, I'll write down those equations. A is 3x plus y plus z equals 4, and C is 6x minus 3y plus 4z equals negative 13. So the y's will eliminate if we take the entire top equation and multiply both sides by positive 3. So if I do that, I'm going to get 9x plus 3y plus 3z equals 12. And the bottom equation stays the same. 6x minus 3y plus 4z equals negative 13. And now when we add straight down, those z's eliminate. I get 15x's, big numbers, plus 7z's equal negative 1. Okay, so there's my second equation. Oh, seniority. Boy, I wrote a nasty problem for y'all. Y'all sound like a Texan here. Because now we have to eliminate something. We have 4 x's and 3 z's. I guess you can read, so I don't need to write this again. Pick something to eliminate. I'm picking the z's because those have smaller numbers. So I'm going to try to eliminate the z's. That means I'm going to take this equation and multiply by negative 7, and I'm going to take this equation and multiply by positive 3. So my first equation multiplied by negative 7 becomes negative 28x minus 21z equals negative 14. That dot's going to drive me nuts. Okay. Second equation, 3 times 15 is 45x. This had better work out. Plus 21z equals 3 times negative 1 is negative 3. Hope. Let's see. 28, negative 28 and positive 45 is 2 and 10 and 5, so that's 17. X. These guys eliminate, and it equals, hallelujah, negative 17. So when we divide both sides by 17, we get x equals negative 1. Yay! X is negative 1. And now to find all the other variables, let's just back our way up. If x is negative 1, this is negative 4 plus 3z equals 2. So 3z would equal, adding 4 to each side, 6. So z must be 2. So x is negative 1, z is 2. And this one looks pretty simple. X is negative 1 minus y plus z is 2, so that's 4, has to equal negative 2. So I get 3 minus y equals negative 2. You could just think about it, or you could do math. What the heck, I'll do math. I'm thinking about it, and I'm thinking y has to be 5, because 3 minus 5 is negative 2. That's okay, I'll do math. I'll subtract 3 from each side. I get negative y equals negative 5, and divide by negative 1. Y equals 5. Hip, hip, hooray. You could always go back and check into all of these equations to make sure that our values work. But they do. We're good. Let's move on to number 7. Number 7. Oh, these problems give people grief. So much grief, I'm going to get some water first. Alrighty. So we're given some angle theta in the second quadrant. So I'm going to draw my, sure, what the heck, we'll draw the unit circle.
And we're over here. Here's quadrant 1, and here's quadrant 2, second quadrant. By the way, here's quadrant 3, and here's quadrant 4. I don't know why they use Roman numerals, but we will. And it says the sine of the theta is 7 over 25. Well, sine is a ratio of sides. And so what we could say that this is a unit circle, and I'm going to take a little aside here, because the fact is, if I have a non-unit circle, and I have this, a sine ratio of 7 to 25, versus this one here, where it's 7, 25ths, and 1. Here's a unit circle. This angle is the same. And it has to be the same because these are similar triangles. All I'd have to do is multiply this, or divide both sides by 25 here, and I'm just shrinking the triangle down to be exactly this unit circle. So when you see problems like the one we've been given, it is most convenient to pretend that this is not a unit circle, but instead is a circle with a radius, say, of 25 and a height there, or radius of 25, so that we can still have the sine of an angle that's 7 over 25. Hey, it's a right triangle. We could find this length. I know that 7 squared plus that length squared has to equal 25 squared. 7 squared, I happen to know, is 49, plus x squared has to equal 25 squared. We could whip out a calculator, but I think it's 225. 25. Doesn't it have a squaring button? Whoops, it has to have an on button first. On. 25. I think that's squaring. Yep, entered. Sure enough, it's 625. Did I say that, or did I say 225? I don't know. Brain and mouth aren't connected. I get 625. We could subtract 49 from each side, and so maybe I'll subtract 49 on my calculator. I get 576. X squared equals 576. And you're not expected to know the square root of that. And wouldn't it be nice if it's just like a really nice number? What is the square root? Can I find the square root button? Oh, there it is in blue. Square root of 576. Oh my gosh, it's a nice number. 24. All right. So we know then that this side has to be 24. There's a little trick here. It told us that we're in the second quadrant, which means this cosine must be a negative value. That said, we can now find the cosine of our angle theta. Cosine is adjacent over hypotenuse. And our adjacent side is negative 24. And hypotenuse is 25. So this is negative 24 over 25. And we can also find the tangent of the angle. The tangent is the opposite over adjacent, or the sine over the cosine, which is 7 over negative 24. 7 over negative 24. And that's it. Moving on. Number 8 rather. Oh, fun. Given the sequence 3, 6, blank. Identify the next 3 terms and figure it out. Well, if it's arithmetic, that means it's an adding sequence. So we'd add 3, so we'd add 3 again, we get 9. We'd add 3 again, 12. Add 3 again, 15. And let's see. I guess we could have a couple of different answers because it depends on whether you think of this as your 0th term or your first term. So if I think that, well, let's see. I'll think of it first as my 0th term. So that would mean, what did we use? Did we use t sub n or something like that? Probably something like that. T of n is grows by 3, starts at 3 and grows by 3n. So that would be with 3 is our 0th term. If 3 is our first term, then we would have to back up because we'd have to start at 0. So t of n could be just 3n plus 0, and that would be with 3 as the first term. And notice you plug in 1 for n and you get 3n. Or you could actually define this thing recursively. You could say t of n plus 1 is, it's the preceding term plus 3, and you just have to say what our 0th term is. That would be 3. T of 0 is 3, and T of 1, yep, that'll work. So a bunch of ways to do that. If the sequence is geometric, if it's geometric, that means it is a multiplying sequence, and we would be multiplying by 2 each time. So it would be 3, 6, we multiply by 2 and get 12, and multiply by 2 and get 24, and multiply by 2 and get 48. The equation for this, again, it depends on whether you have 3 as a 0th term, or 3 as a first term. So if we want 3 to be the 0th term, I would say the equation is t of n equals, that means I plug in 0 and I want to get 3. So how about 3 times 2 to the 0, or to the n rather, because I'm multiplying by 2 every single time. So we plug in 0, we're going to get 2 to 0 is 1, we get 3. If 3 is the first term, then there are a couple of ways we could write that. We could write t of, well, that means if we plug in 1, we want to get 3. So we could say it is, boy, let me think about this a little bit. Well, I thought about it, and let's see, I'm thinking if we plug in 1, we want to get 3. So 3 times, and this thing needs to be 1, so I could say 2 to the n over, oh, let me think about this again, sorry guys. Well, I vaguely remember in this chapter that, oops, sorry, I was writing my answers. I vaguely remember that there was a way to change the initial value, but I'm just going to go for this, my default cheat, where if I plug in 1, I'm going to want it to be 3 times 1. So if I write 2 to the n minus 1, then t of 1 is going to be 3 times 2 to the 0, which is 3. And t of 2 is going to be 3 times 2 to the 2 minus 1, which is 1, which is still going to be 6. So that will also generate this sequence. All right. Also, we could have defined this recursively. You could have said t of n plus 1 is going to be the preceding term, t of n times 3, or times 2 rather. And then you would have had to say that t of 0 is 3. That's a little bit easier, actually. All right, hey, moving on to number 9. Number 9. Hey, you haven't seen this really yet, so I tried to give you a little hint. One, I told you that it's a circle. And you can tell it's a circle because it's got an x squared and a y squared. Circles, when we graph them, look like this. X minus h squared plus y minus k squared equals radius squared. And what we have here is we have a perfect square and another perfect square. So here's a little hint. You're going to have to complete the square 2 times. And the first step for doing this is to do what I did here, and that is get the x terms together, that x term with that x term, and get the y terms together. Oh, and not make typos. It looks like I have 111 here, and that's just crazy. I don't know where that would be. I would have to subtract 11 from each side. So this should be negative 11. Oh, I see what happened. That 1 got turned sideways. Just take this 1, turn it sideways, you get negative 11. Joke. So, pardon the typo. So x squared minus 8x plus y squared plus 6y equals negative 11 at this point. And I'm actually going to clean this up. Equals negative 11. So I want to make this a perfect square. So I could draw the square if you need to. Let's see, I have an x squared. I have 8 negative x's, so I'll put 4 negative x's in each corner, which means we have x, x, negative 4, and negative 4. So to make it perfect, we need a 16. So I'm going to go ahead and add 16. But I can't just go adding 16 wherever I feel like it. So what I'm going to do is also add 16 to the other side. And let's take a look at this thing. I want this thing also to be a perfect square. And so if you had to draw the square, if you know it's 9, great, skip ahead.
It's y squared and 6y, so I'll split it up to 3y and 3y. So my sides would be y and 3 and y and 3, so it'd be 9. So plus 9. But I can't just go adding 9 to each side, so I'm also going to add 9 there. Let me pause. Alrighty, but now we have a couple of perfect squares. This thing here is an x minus 4 squared, x minus 4, whoops, times x minus 4. And this thing here is a y plus 3 squared. And over here we have negative 11 and 25. So negative 11 and 25 is 14. So there we have it. It probably says identify the center and the radius. Well, my center is my HK on this guy. So the center is going to equal 4, comma, negative 3. And the radius, this is supposed to be r squared. My r squared must be 14. So my r must be the square root of 14. Not a very pretty number, but there it is. Radius equals the square root of 14. Number 8. It says we're for each of the following, basically fill in the table, showing that you know where all these angles are. So let's see, 120 degrees. I'm going to start with a picture. 120 degrees is, well, here's 90, so it's 30 degrees past it. It's right over there. So there's my 120 degrees. And that seems kind of special. This is a 60-degree angle here then, 60 degrees. So it's a special triangle. In pi form, 120 degrees is, well, here's 1/3 is 60, 2/3 and 3/3. So I'm going to say this is 2 pi over 3. To find out in radian form, that's a calculator problem. Incidentally, here's pi over here, and pi radians is 3.14 radians. So really, it's just converting pi form into a decimal. I don't want that one, I want this one. So to do that, we would say what is 2 times pi, and then divided by 3. 2.09 radians, okay? 2.09. Okay, and the cosine of the angle is this short side. The cosine of the angle is 1/2. Oops, it's backward 1/2. And the sine is that height, and it is up root 3 over 2. Number B says if we have 1.2 radians, how many degrees is that? All right, well, if I have 1.2 radians, and I want it in degrees, I need to multiply by degrees over radians. I happen to know that 180 degrees is pi radians. And notice it says we're not going to have to find this in pi form. It's x'd out. So let's just do the math and get this in degree form. I'm going to grab a calculator. So it's 1.2 times 180 divided by pi. And enter. 68.75 degrees. It's just not pretty. 68.75 degrees. And let's see, 68.75 is not special. I can draw a circle or put it on the circle. It's somewhere like here-ish there. 68.75 degrees. If I want to find the cosine of that, here's how I do it. I go to my calculator. I say, what is the cosine of 68.755? And it tells me it's 0.36. 0.36. And the sine of 68.755. Enter. 0.932. 0.932. That's just ugly. Is that the only one that's ugly? Yep. Well, yeah, that's the only one that's ugly. Number C. They gave us 3 pi over 2. Whoops. Well, I'm going to start with a circle. 3 half pies. Well, here's pi. So here's 1/2 pi. That's 90. 2 half pies. 3 half pies is down here. So this is 3 pi over 2.
So that would be our angle. We want to know how many degrees around that is. This is 180 degrees plus another 90, so I'm thinking that's 270 degrees. How many what that is in terms of a decimal, come back, little calculator. It's 3 times pi, oops, not divided by, times pi divided by 2. 4.71 radians, sure, 4.71 radians. And then it says find the sine and the cosine of that. We can do that part without a calculator because the sine is the y value, and my y value in the unit circle at that point is -1, and the x value is how far back and forth we've gone, and that x value is 0. Number D, 225 degrees. All right, well, 225, I'm first going to put it on a circle and see where we are. Here's 180 degrees, and so 225 is past that, and it is past that by a 45-degree angle. So 225 is that distance. Looks like that's kind of special. It's a 45, 45, 90. And so the sides are going to be root 2 over 2 and root 2 over 2. And this is a backward value, so that's negative, and this is a down value, so that's negative. Oh, we just found the sine and the cosine. Let's see, 225 degrees, we need to change it to pi form. Well, a 45-degree angle is 1/4 of the pi, so that's 1/4, 2/4, 3/4, 4/4, 5/4 pies. So I'm going to call this 5 pi over 4. Change that to a decimal. Let's get our calculator friend and ask them what is 5 times pi divided by 4. It tells me it's 3.93. 3.93. And let's see, the cosine. Cosine is the back and forth at this point, which is negative root 2 over 2. And the sine is the y value, the up and down, and that is also negative root 2 over 2. It's fun. And last but not least, 11 pi over 6. Well, let's see. I know, well, what the heck, I guess this diagram is supposed to be in there. I know that pi is 180 degrees. Pi radians is 180 degrees. And so pi over 6 is 180 divided by 6, which is 30. Pi over 6 is 30 degrees. And if I want 11 of them, that means I'm multiplying that times 11. And 11 times 30 is 330 degrees. 330 degrees, oh, there's my angle measure. 330 degrees. We'll change it to a decimal, sure. What is 11 times pi divided by 6? Enter. 5.7595 radians. How about 5.76 radians? Okay. And now we want to find the sine and the cosine there. I need to draw it. It's actually 330 degrees is 30 degrees down here. So drawing this bigger, we have again, a 30, 60, 90, where we do know the sides. This hypotenuse is 1. The short side, if it's drawn to scale, is a half, and the long side is root 3 over 2. So we can find the cosine. Cosine is the x value, which is forward root 3 over 2. I don't know why I was drawing negative, because it's a positive root 3 over 2. And the sine is that y value, which is down, so it's negative 1/2. And that is the end of that problem. Here we are at number 10, doing a little bit of graphing. And so we're supposed to graph this crazy function. Well, let's start with a period. Period is the b value with a b value of 1. My b value is 1, so that means my period is exactly 2 pi. That's easy. The locator is hk. Our h is 3 pi over 4, but it's going to be negative 3 pi over 4. and the k is -1, and the amplitude is our a value, so that would be 1. Okay, so let's graph a sine wave. Since my locator is at 3 pi over 4, I'm thinking I want to count by a multiple of 4. So I'm going to let pi, let's pause. Alrighty, I'm going to let pi be 8 boxes. So here's 4, and here's 8 boxes, and I'll label that pi. And here's 4, and here's another 8 boxes, so that would be 2 pi. And here's 4, another 3 boxes, that's 3 pi. Can I fit it? 4, just barely. Does it fit right there? So that would be 4 pi. I can go backward. This would be negative pi. Okay, so if pi is 8 boxes, 3/4 a fourth pi over 4 would be 2 units, or 2 boxes. And so 3 pi over 4 would be 6 boxes. So here's 1/4 pi, negative half, 2/4, negative 3/4. So here's -3 pi over 4. And I'll just go ahead and mark off quarter pies. 1/4, 2/4, 3/4, 4, 5/4, 6/4, 7/4. Oh, did I miscount? I'm an idiot. Hopefully you didn't copy me. Let's see. Shows what you get when you eyeball things. Okay, that's 8/4, 9/4, 10/4, 11/4. There's 12/4 pi, also known as 3 pi. 12/4, 13/4, 14, 15, and 16/4, also known as 4 pi. Okay, so it's scaled off. I'll count by, what the heck, I'll count by 2's. Sure, I'll let this be 1, and let this be 1, 2, this be 3, -1, and -2. All right. So if we're graphing this sine wave, let's start by plotting a locator. The locator is at -3 pi over 4, -1. Keep in mind, here's what sine waves look like. They start, they go up, down, back, and then they finish. So they start at the locator. So I'm going to put my locator at, I'm going to clean this up for a second. Can I make it cleaner? There we go. This is -3 pi over 4. So I'm going to start at my locator, which is at -3 pi over 4, -1. That's the start point. We're going to finish one cycle later, or one period later, which is 2 pi. So if we made pi 8 units, that means we would finish 16 units later. So there's 8, and there's another 8. So we should finish right here. So that's going to be my ending point. Halfway between the beginning and the end, there's a middle point. So that means the middle is going to be right there. Halfway between the beginning and the middle, we're up 1 amplitude. So halfway between these 2 points, we're up 1 amplitude. And halfway between the middle and the end, we're down 1 amplitude. So halfway between these 2 points would be down 1 amplitude. And we can make it look all wavy. There it is. And we can continue the pattern. Let's see, it looks like I'm 2 boxes up and 4 over. So over 4, up 2, down 2 over 4, down 2 over 4, up 2 over 4. We'd go up again. Now if you continue making it wavy, you didn't know you were going to get sound effects with this, did you? Okay, well, we've graphed a sine wave. Now it's time to label these things. And notice that every one of the dots is labeled at increments of 1/4 pi. So this is -1/4 pi. This is +1/4 pi. 2/4, this is +3/4 pi. 4/4, this is +5/4 pi. 6/4, this is +7/4 pi. 8/4, this is +9/4 pi. And I think we've labeled at least one cycle. We labeled one cycle completely. Yay! Let's move on to the next one. Yeah.
Okay. All right, we have, ooh, good. I did give you a cosine. I don't remember doing that, but we needed to put the cosine wave. Okay, so first let's figure out the period. We have a b value again of 1, which means the period is going to be 2 pi. That makes things convenient. No stretches. No horizontal stretches in any event. Let's see, an amplitude is the a value, whoops. Amplitude is an a value, which is, you could call it -2. You could also call it +2, because remember, amplitude is an absolute value. It's a displacement. It's a displacement from a center line. Okay, so my center line is going to be 2 one way or the other. I just started graphing this thing, and I want to undo that because I want you to keep in mind what cosine waves look like. Cosine waves start up, go down, back, and up. And they have a center line like that. So, and the reason that happens, just if you're watching this video, the reason that happens is because the cosine is our back and forth value as our little friend Hank travels around the circle. And so as Hank travels around the circle, when he starts on the ride, he is at +1. So when he is 0 degrees around, he is at +1. And then as he travels around the circle at 90 degrees, or at pi/2, he's at 0. So this is 90 degrees, or pi/2. His x value is 0. And then as he keeps traveling around, here he is at 180 degrees, and his x value is all the way backward 1 unit. So here at 180 degrees, which is also called pi, his value is at -1. All right, so that's why cosine waves look a little bit off from sine waves. They're just shifted sine waves. But in any event, our parent graph of a cosine wave looks like the one that I sketched here. Okay, let's find a locator. Locator is going to be hk. My h is 5 pi/6, and the k is 0. Alrighty. Because we're starting at 5/6 pi, I would really like to make sure that we make pi a multiple of 6. So I'm going to go ahead and pause this. All right, so just to be safe, I'm going to let pi be 12 units, because I know that I can divide that into 6 pieces very easily. So, and this time I'm going to count carefully. 2, 4, 6, 8, 10, 12. So I'll make that pi. I might not be able to fit 2 full cycles, but that's okay. 2, 4, 6, 8, 10, 12. That's 2 pi. 2, 4, 6, 8, 10, 12. That's 3 pi. I wonder if I can go back 12. 2, 4, 6, 8. No, I can't. But I can go back 6, which would be -1/2 a pi. And I can go forward 6, 2, 4, 6, and that would be 2.5, or 5 half pies. So we'll manage to get 1 cycle plus. Okay, let's start by plotting a locator. The locator is 5/6, 0. Well, if pi is 12 units, looks like I could have counted by 6s. Pi over 6 is going to be 2 units, so that's 2 units. And 5 pi over 6 would be 10 units. So every one of these little increments is 1/6, 1/6, 2/6, 3/6, 4/6. Here's 5/6 pi. And what the heck, I'm just going to go ahead and label all of my bunch of points right now. Maybe we can make my pen small enough that it's legible. Okay, so this is, hey, this is 5 pi over 6. Go away, thing. Why is it not letting me go away? Now it's probably going to be a fat pen. It's 5/6. Here's 6/6. Here is 7 pi over 6. 8/6, 9/6, 10/6. Maybe I'll save the labeling for later, but in any event, what are we doing here? Cleaning up, wishing that my pen could stay skinny. Okay, so we plotted the locator. There it is, 5 pi over 6, 0. Note that a locator for a cosine wave is not actually on the wave. The locator, if this is my graph of y equals cosine of x, my locator is at 0, 0, but the green dot isn't even on the wave. It's just telling me where the center line of the wave is. So we started at 5 pi over 6. We need to finish the first wave 2 pi later. That's 24 boxes later. So, well, this would be 1 pi. And to get to 2 pi, oh, I hope I can do it. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. Good. We're going to finish right there. So from here to here is my wave. And notice this is just the center line of the wave. To graph a cosine wave, now I've got a center line. There, we've got a center line. The first thing we do is start up one amplitude, but our amplitude is negative. Well, our amplitude, our A value is negative. So instead of starting up one amplitude, we would start down one amplitude. So I'm going to count by 2s. Here's 1, here's negative 2, here's positive 1, here's positive 2. So I would start down 2, and then we have a start. Now we need to finish. So we're going to finish 2 pi later. Oops, I shouldn't have made that dotted line there because that makes it look like a center line. So we'd finish 2 pi later. So I'm going to finish there. Halfway between the beginning and the end, in the middle, we should be down. See, I'm drawing over here, down 1 amplitude. So here, halfway between would be at this point, and here we should be up 1 amplitude. So we've got a beginning, an end, and a middle. Halfway between the beginning and the middle, the cosine wave is on the center line. So halfway between here and here, it's on the center line. Halfway between the middle and the end, it's also on the center line. Yes, I did just graph this with Argonaut colors. Here, let's go back and fix that. There, go big blue. There we go. Alrighty, and we've got ourselves a cosine wave. Yahoo! Alright, I could continue the pattern. It looks like it's 1, 2, 3, 4, 5, 6 boxes over, 4 up. So if I go back 6 boxes, 2, 4, 6 boxes, up 4, back 6, 2, 4, 6, down 4, back 6, 2, 4, 6, right there. And so we continue this thing, and it looks all cosine-y. We now need to label a complete cycle. So let's find ourselves some points. This is 1/6, so this is 2/6 pi, but you really shouldn't leave that as 2/6. You should reduce that. 2 divided by 6 is 1 pi over 3. So this is pi 1/3. 2, 6, 3, 6, 4, 6, 5, 6 is already labeled. 6, 6, 7, 6, this is 8/6. 8 pi over 6, but 8 and 6 also reduced to 4/3. So this point here is 4 pi over 3. 8, 6, 9, 6, 10, 6. This is 11 pi over 6. 11 pi over 6. 12, 6, 13, 6, 14, 6. So this is 14 pi over 6, but again, they're both even, so let's divide them and make it 7 pi over 3. 7 pi over 3, and we have done more than one complete cycle. I could go backwards and label this negative pi over 6. All right, we're done. We made it. Whew! Number 11. Develop some equations. All right, well, let's first figure out a period for ourselves. Let's see. Here's pi. 2, 4. It looks like they're counting by 6s. And we started a wave there, and we finished a complete cycle right there. And if I were to ask you what wave I just graphed, hopefully you would say that's a cosine wave. We could count how many boxes that is, but it looks to me like 6, that's 12 boxes. And pi is 6 boxes. So that means my period must be 2 pi. That's convenient. That means the b value is 1 again. Alrighty, the amplitude is the displacement from the center line. And so I would need a center line here. Let's see. This is up at 1. This is down here at -3. So I'm thinking my center line is there at -1. So my amplitude is that displacement, and in either direction we are displaced by 2 units. Okay, and a locator. People, there are infinitely many locators that you could choose from. Oh, whoops, I should have edited this worksheet. I should have edited this worksheet to say a locator for sine, and a locator for cosine, because they're going to be different. So let's find ourselves a sine locator. If we're looking for a sine locator, we're looking for a wave that looks like this. Starts, ends, and goes up and down and back. So I could say I could start at that point, at which point I could finish at this red dot. This would be one positive sine wave. If I wanted, I could have started at this point and graphed one negative sine wave. But I like the red one, so I'm going to stick with that. So I'm going to choose as my locator this point, which is, let's see, pi is 6 boxes, so each 2 boxes is 1/3 pi, so this is negative pi over 3. So my locator is negative pi over 3, comma, -1. And now I'm ready to write an equation. Sine wave would be y equals a to sine of b, and we'd have a b value of 1 because the period is 2 pi, x minus h, so plus pi over 3 plus k minus 1. Now if we wanted a cosine locator, let me grab the red wave because the red is a sine wave. Pretty close. That black graph makes a darn good cosine wave. But the cosine locators, again, have to be on the center line, because remember that cosine starts up, comes down, goes back, and the locators for cosine waves are on center line. So I'm going to choose this point here, this point right there, and since we're counting by 6s on this thing, I'm thinking one box is 1/6 pi, so this is pi over 6. So the locator, cosine locator, is pi over 6, comma, -1. So the cosine equation would be y equals 2 cosine x minus pi over 6 minus 1. Alrighty. Number 12. Is this the last problem? Sure is. Here we go. Number 12. Find all the values that make this true. These are tricky. So this says the sine of the angle has to be -1/2. So that means we're looking for some angles where the y value is -1/2. And right here, the y value is +1/2 when I have a 30-degree angle. So if I wanted my y value to be -1/2, I'd want to go down here. I'd want to have a -30-degree angle. But by the way, the angle has to be between 0 and 2 pi. So I could say over here, this angle has a -1/2. We'd have to find out how many radians it is. We have 30-degree angles. 30 degrees, that's 180 degrees divided by 6. 80 degrees divided by 6, so that's pi over 6. So every 30 degrees is 1/6 of pi. 1/6 is half. 2/6, 3/6, 4/6, right? 3 pi over 6 is half pi. 4/6, 5/6, 6/6. This is 7 pi over 6. So at 7 pi over 6, my angle could be 7 pi over 6. And then I'd also like to find out this angle. So I'm going to keep counting in 6. 7/6, 8/6, 9/6, and that should make sense because 9 pi over 6 is 3 half pies. 9/6, 10/6, and this is 11 pi over 6. So 6. Alrighty, B. Where is the sign root 2 over 2? Alright, well, for starters, the sign is a positive value. So we have a positive y value that's root 2 over 2. That seems special. Seems to me like that's a 45, 45, 90. So maybe if this is a 45-degree angle, 45 is 1/4 of pi. So this is a pi over 4. And sure enough, at that point, we would have a sine, a y value of root 2 over 2. So my theta, my angle, could be pi over 4. But wait, there's more, because I could be over here, right, where my height, my y value, is also root 2 over 2. And that would be 1/4, 2/4, 3/4 pi, or 3 pi over 4. Number C says, where's the sign negative root 3 over 2? So again, I'll draw my unit circle. That means, again, this looks kind of special. I think that's from a 30, 60, 90. And that would mean it's the long side of a triangle. So like that long side there. So negative root 3 over 2 would be negative 1/2. We want to find that angle. And if I'm not mistaken, that is this yellow angle right here is 60 degrees. And every 60 degrees is 1/3 of pi. So here's 1/3 pi. Another 60 degrees is 2/3 pi. And then that means this angle here, this one here is 3/3 pi, also known as pi. So this angle is 4/3 pi. So that's one answer. 4 pi over 3. And I could have the same y value over here. Okay, I've got the same. There, make the triangles look the same. So here my y value is also negative root 3 over 2. And that's just a little bit later. It's just another 60 degrees later. So another pi over 3. So this would be 5 pi over 3. Should make sense. You go another 60 degrees, you're at 6 pi over 3, which is at 2 pi. So the other angle here is 5 pi over 3. And last but not least, where is the sign or the y value 0? All right, well, that means my height has to be 0, which is basically when Hank is at ground level. So, well, that happens right at the beginning of the ride when my theta is 0. It happens again. Come on, Hank. It happens again right there at pi. And it happens again at the end of the ride at 2 pi. So my answer is, theta could equal 0, pi, or 2 pi. I hope, Algebra 2, that this has been a useful video for all of you.